Hello everyone. In today's video lecture series, we are going to solve one of the most frequently asked question from digital design, that is how to implement a complete 2:1 MUX using only NAND gate. We will also solve the same question using only NOR gate. So let's start with using only NAND gate. So before starting the implementation, let's quickly revise how the 2:1 MUX works. So as you all know, this is the symbolic representation of 2:1 marks. If there is two input, let's suppose first input as A and second input as V, then based on the select line, let's suppose select line is S, then based on the select line input, the output will decide. So how we will write the output expression? This will come like this. If the select line is 0, then the MUX will select input A, and if select line is 1, then MUX will select input as V. If I will talk theoretically from where this expression is coming, so as you all know, based on the input and output, we used to draw the truth table. So I have drawn one truth table here. So you can see here the number of possible input and output. As we can see, if select line is 0, then the output is A. If we will observe in the truth table, then you can clearly see. And if the select line is 1, then the output is V. So we have just draw this truth table, and based on this truth table, we used to draw the K-map. You can see in the slide as well. And from this K-map, if you will solve this K-map, then you will get this expression. So just now we have seen from where this is coming, and we know the fundamental and the working how the 2:1 MUX works. Now let's move towards the question. So we will implement this expression using only NAND gate. So now let's start. So as you all know, what is the symbolic representation of NAND gate? So if there is two input, let's suppose first input is A and second input is V, then we will get the output of NAND gate as A into V whole complement. So our task is here to implement this, means the MUX output expression using this NAND gate output expression, so that we can say we have implemented the 2:1 MUX using only NAND gate. So for that we need to first observe the output expression of MUX. So what is the output expression of MUX is Y is equal to S complement into A plus S into V. Now if you will observe the output expression of NAND gate as well, then if you will see, there is no plus sign present in the output expression of NAND. So as you all know, if you will apply the De Morgan's theorem in the output expression of NAND gate, means here if you will expand this A into B whole complement, then we know we will get this A complement plus B complement. Now if you will observe the output expression of NAND gate as well as the MUX, then there is a similarity. One plus sign is present in NAND gate expression as well, and one plus sign is present in the MUX expression as well. So remember one thing, whenever you are implementing any Boolean circuit using only NAND gate, then try to convert the implemented expression in SOP format, because the NAND gate produce the output naturally in SOP format. So if you are able to convert the output, implementing output in a SOP format, then it is easy to implement using NAND gate. So now let's implement this circuit. So we need to implement this using this. We have converted the NAND gate output in the similar to the MUX output expression. So let's assume this as P, means P is S complement into A, and let's assume this second term as Q. So you will get the clarity why I am assuming. So let's assume the Q as V into P, sorry, S into B. Okay. So now tell me one thing, if I will pass these P and Q, means if I will pass the P and Q through the NAND gate, then I will get Y as P complement plus Q complement. Tell me one thing, we need not complement only P, because we need this expression here, P plus Q. So if I want, instead of P, so P complement P, and instead of Q complement Q, then if I will provide here the input, complemented input, means instead of the normal input, if we will provide the complemented input P complement and Q complement, then the output can I get like this, like uh, P complement into Q complement and whole complement. Then you all know, if I will apply the De Morgan's theorem here, then what will happen? This P complement and Q complement further comes in a double complement form. This double complement will cancel out and we will get the P plus Q. That is all we are going to implement here, because we just now we have assumed P as S complement into A and Q as B, S into V. So now our task is to implement this P and Q. Sorry, P complement and Q complement. So what is the P complement? So P complement is nothing but this is S complement into A and then whole complement. Similarly, Q complement, what is the Q complement? S into V whole complement. Now let's implement the P complement and Q complement individually. So what is the P complement here is S complement and into A and whole complement. So now tell me one thing, if I want to implement this means P complement, then what I need to change in the output or input expression of NAND gate, so that I will get the output expression of this NAND gate as P complement. So let's suppose this is A and V, then as we all know, we are getting the output expression of NAND gate as A into V whole complement. Now tell me one thing, if I want, instead of this, if I want S complement into A and then whole complement, then what I need to change in input, so that I will get here as S complement into A and then whole complement. So if you will clearly observe, then A is same here. What is the change? Only V. So instead of V, if I will apply here as S complement, then can I will get this as the output of NAND gate? Okay. So what I will do here is, instead of this V, I will apply here as S complement. Now, if you will observe here, I need to apply the S complement. So I will first make the S complement with the help of NAND gate, and later I will connect the output of that gate to provide the complemented input to this NAND gate. So as you all know how the NAND gate treat as a NOT gate. So if you will connect these both input leg to the common input, means if we will connect these both input of NAND gate through a common input, then we will get the output as complemented output. So this will treat like a NOT gate. So in the similar concept, we will convert this as in a complemented form. So what will be the final look of this circuit, means P complement. Here you will get the output expression as S complement into A and whole complement. Okay. So here we have implemented the P complement. Now let's implement the Q complement as well. So what is the Q complement? Q complement is nothing but S into B whole complement. So let's implement this as well. So this is very simple as compared to the Q complement. As you all know, if there is two input A and V, then we will get the output as Y is equal to A into V whole complement. Now this is very simple, like we need only, instead of this A into V complement, we need S into V complement. So what we need to change in the input, so that we will get this as the output instead of the A into V complement whole complement. So V is same, just we need to replace S with A, then we will get the Q complement as the output. So we will replace this S with A with S, and here we will get the output of this NAND gate as Q complement. Now we have P complement and Q complement as well. So in starting only we have seen, if we will connect the Q complement and P complement, through the 2-input NAND gate, then we will get the output as MUX output. So that's all we are implementing here. Now let's connect the Q and P complement to make the complete implementation of MUX using the NAND gate. So what is the output here? We will get S complement into A plus S into V. Okay. So that's all we are implementing here. So how many NAND gate required if there will be a question in interview and any test? How many NAND gate required to implement the MUX 2:1 MUX? So then we can simply write the output as 4 NAND gate required to implement the 2:1 MUX. Okay. Now let's move towards the next question. So the question is same. We need to implement 2:1 MUX, but here we will use only NOR gate. In previous question we have used NAND gate, and we will implement here using only NOR gate. So for that, first we will write the output expression of NOR gate. So this is the NOR gate symbolic representation. As you all know, if there is two input A and V, then we will get the output expression as A plus B and whole complement. And also we will write here the MUX output so that we will get the clarity. So this also, you know, if there is two input A and V and the select line as S, then we will get the output as S complement into A plus S into V. Now remember one thing, whenever you are implementing any circuit using only NOR gate, then one thing keep in your mind during the implementation of any circuit using only NOR gate, first try to convert the expression or the circuit output that you are going to implement using only NOR gate in the POS format. Why I am saying this? Because as we have seen in the last NAND gate implementation as well, the NOR gate produce the output naturally in POS format. So if you will convert the expression that you are going to implement using NOR gate, that expression if you will convert in the POS format, then that will be easy to implement using NOR gate. So keep these two things in your mind during the only NOR gate and only NAND gate implementation. So what is the two things? So for NAND gate implementation, first try to convert the output in SOP format, so that the NAND gate, because the NAND gate output produce naturally in SOP format, so that the implementation using NAND gate will be easy. Similarly for the NOR gate, try to convert the output that you are going to implement in POS format, so that the implementation will be easy. So now let's see how we will convert this format. Like this is currently in SOP format, sum of product format. Now we need to convert this SOP into the POS format, so that the implementation using the NOR gate only will be easy for us. Now let's convert this expression into the POS format. So there are several methods to convert SOP to POS, but the KMap method is easier as compared to the others. So what we did here, instead of the ones, we will make the combination of zeros, and then we will write the output expression in the POS format. So what will be the output come from this KMap? That will come A S, because S is coming from this side and a common part from this area. So what is the common? A. So what we will write here, S plus A, and this is the POS format. So after this the dot will come, and next write the next term. So what is the next term? S complement, because here if you will see, one is here. So in POS, one represent the complement, and from these both we will see the common part. So what is the common in these both? B. So we will write here V. So this is the POS format or POS conversion of this expression. So now if you will observe this NOR gate expression and this expression, POS expression of the MUX, then these both expression looking somewhat similar. And if these both are similar, then implementation using only NOR gate will be easy. So now let's see the implementation using only NOR gate. So as we have the equation of the MUX in POS format, S plus A bracket into S complement plus B. This we need to implement using only NOR gate. So as you all know, whenever we are passing two input through the NOR gate, A and B, then we will get output as A plus B whole complement. Okay. Now we need S plus A. So what we will pass through this NOR gate? S and A. What we will get here? S plus A whole complement. Okay. And in the second term, if you will observe, then we are getting here S complement plus B. Now in the similar concept we have did in the NAND gate implementation. So what we will do here, we will first convert the S into the S complement. If we will provide the complemented input as S complement here, and then output we will connect through one more NAND gate input, and here we will give the V, then we will get here S complement and V, because in the output expression of the MUX we are getting S complement plus V. So for that we need to also arrange the input combination like that, so that we will get here as the second term. Now these both term we will connect through the next stage NOR gate to get the final output. Now what you will get here? S plus A complement plus S complement plus B whole complement. Sorry, this will be a whole complement. And again, because of this NOR gate, complement will come because of this NOR gate. Now we will use the De Morgan's theorem here as well. So what the De Morgan's theorem will say, if you will change this plus sign into dot, then one more complement will present in each the term. One is already presented and one more will come because of the De Morgan's theorem. Then these both complement sign will cancel out and we will get here the final output as MUX output. So that we will get here the MUX output as the final output. Now from this we can say we have implemented the our MUX 2:1 MUX using only NOR gate, 2 into NOR gate. So if you will simplify this circuit, then we can also rewrite this circuit like this. Now if you will see, we have successfully implemented the 2:1 MUX using only NOR gate. So similar to the NAND gate implementation, if some question will ask from this NOR gate implementation 2:1 MUX, then we can simply write the answer 1, 2, 3 and 4. 4 NOR gate required to implement the 2:1 MUX, and the 4 NAND gate as well we have seen required to implement the 2:1 MUX. Now we have completed 2:1 MUX implementation using only NAND gate and also using only NOR gate. Thank you everyone for watching this video till end.